Okay, let's start. So today we'll go into the center of out-of-order pipeline. So all commercial microprocessors implement a form of Thomas law algorithm to implement this dynamic pipeline. And this algorithm is proposed in 1967 for IBM 360. This is a famous machine. They are famous for their operating system, their disk operating system, and so on. The algorithm had three ideas. It used reservation station. As I said, in out-of-order pipeline, the instruction behind sometimes bypass instruction ahead of it, right? To avoid pipeline stall. So the instructions waiting for source have to wait in the instruction window. This is a kind of instruction buffers. And reservation station is a distributed instruction window. So there is not a single central window. Every functional unit has its own instruction window, and it's called the reservation station. So when you issue instructions from decode stage, you actually send instruction to reservation station that corresponds to that functional unit. So if the instruction is integer operation, you are sending instruction reservation station. If the instruction is floating point instruction, you are sending the reservation station that are attached to the floating point unit and so on. Okay? So they use distributed instruction windows. So distributed instruction window means it's more scalable compared to central window, because as the window size become bigger and bigger, there are lots of complexity which can increase the CPU cycle time. But distributed instruction window means it's decentralized and the size can be reduced compared to centralized instruction window. And the second characteristic is they use register renaming to remove anti and output dependence. So we have discussed three types of data dependence. And read after write dependence is called true data dependence because you have to wait. There is a producer-consumer relationship between producer and consumer. But the other two types of register dependence, such as write after read dependence or write after write dependence, can be avoided if you have many storage, many registers. The problem occurred, the complication occurred because you are sharing the same register. For example, write after write dependence, you are trying to write to the same destination, and sometimes the first instruction, writing to register R1, takes too long, and if you allow second instruction go ahead, second instruction can update R1, and later the first instruction override R1, which can cause problem in the later instruction. Okay? But every write, if you allow the second write to write to different register, such as R10, then there is no sharing, and you can avoid this problem. Okay? And the same applies to anti-dependence, right? To read dependence. This instruction is trying to write after read. This instruction is trying to read source, and this instruction is trying to write to the same source, and there is no producer-consumer relationship. Okay, this is read, and this is write, right? So write and read, there is a read after write dependence, but read and write, there is no producer-consumer relationship. So you are worried about future write, okay? But if you allow in out-of-order pipeline, if you allow the second instruction to bypass this instruction before this instruction is reading the source, this instruction can bypass and override this source so that the first instruction is reading the future value of this source instead of the previous value. So that can cause problem. So in this case also, this write, if you write to different location, then this kind of problem can be avoided. So these are all force dependence, and this can be avoided by register renaming. The register renaming, the principle is a single assignment rule. Single assignment rule means every write you are writing to a new register. So if every write is writing to a new register, you can avoid all these write after read or write after write dependence because there is no sharing. Okay? So if you have a pool of many registered, physical registered, every time you are trying to write, you can allocate a new register to an instruction. Okay? Then you can eliminate all this write after read or write after write dependence. And the same applies to their register renaming. So in fact, in this reservation station, there is a storage for source and destination. Assume that you have two source and one destination for each instruction. In the reservation station, they allocate two source and one destination for each reservation station. And you do not wait in the instruction window until all the sources are available. If the source, one of the sources is available, you read this source of operand from register file directly and store them into the reservation station. Okay? Then you can remove this write after read dependence because, as I said, this is a read and write. It hasn't read the source, hasn't read the source, right? But so the later second instruction can override, and this instruction can read the wrong value, which is the future value. But when it's waiting, it's not that it is not just waiting. It's reading the register from the register file. It put it into its own storage in the reservation station. Then whatever it's writing is nothing to do with this read. Okay, so they can remove this write after read dependence. Okay, so they read available input operand from register file and store them into the reservation station, and they can eliminate write after read dependence. And they also allocate new storage for write after write dependence. So every time you write, you can write into this storage. Okay, so if you have two write, this takes too long, you can allow this instruction to bypass, and whenever it's writing to its own destination. Okay, it does not have to worry about this first write because there is no storage conflict. So pipeline does not store on write after write and write after read dependence. Okay, in Thomas-Ull algorithm. Okay. And the third characteristic is they implement data bypass using the common data bus. So after the functional unit produces the data, they bypass the data directly to the waiting instruction in the reservation station. So they can accelerate read after write dependence by bypassing. Okay? So both register file and reservation station monitor the result database bus, and whenever the data is available, they look at the register ID. Okay? If there is a match, then they update the data in the reservation station or register file. So they can accelerate read after write dependence as well. Okay? That's the main idea of Thomas-Ull algorithm. It's quite easy. Okay? So let's look at the pipeline stage for Thomas-Ull algorithm. So decode, the second stage can be called decode stage or rename stage or issue stage. You decode and issue to the reservation station. You send instruction to the reservation station. You check structural hazard. You have to know whether there is an available entry in the reservation station, right? If your instruction is floating point instruction, you are trying to send this floating point unit reservation station. Reservation station is a buffer, so there should be an entry, right? We check this structural hazard, and at the same time, if source operands are available, you read all these available operands from register file and store them into the reservation station. Okay, so you can remove write after read dependence. Okay, and you also, in the reservation station, there is a storage for the destination as well. So you can remove write after write dependence also, because each entry in the reservation station, there is a storage for source and storage for destination. Okay, and read stage or register read stage means they are waiting in the reservation station until the data is available in the data bus, and then they can match and they can bypass. After them, they are ready to execute if both source operands are available. Then based on the priority, if it's 4 issue, maybe 4 instructions will be dispatched from reservation station to functional unit. Okay? So read stage, they monitor the common data bus and read operand into reservation station if there is a match in the common data bus. And they determine highest priority operation among ready operation. They wake up. Okay, sometimes you can issue only 4, but there are 5 instructions are ready to fire, ready to dispatch. You should select 4 out of 5 based on this priority. And execute stage, you execute, you compute, and the result you put it into the common data bus, and it will be bypassed to the reservation station and register file. Okay? It's quite clear. Okay? So, if you look at the textbook, they have all the tables of detailed management, how you maintain register number and how you do the matching and so on. But the basic idea is this. Okay, so if you know this, you can implement. You don't have to go through that much complexity, but maybe you can do it for your exercise in your homeworks. So, in out-of-order pipeline, there are different types of instruction buffers in the pipeline before you dispatch to the backend function unit. So there can be an instruction queue between fetch and decode stage. This is decoupling queue between front end and back end. As I said, in Itanium, by having this queue, you can improve integer performance by about 8%. Okay? Because front end doesn't have to be stored. Even though back end cannot consume, they can put it into the instruction queue. Okay? Still. Sometimes front end is stored. They are waiting for the instruction cache miss. But the back end can still consume instruction from the instruction queue if the instructions are available in the instruction queue. So it provides some kind of buffering between front end and back end. So they can decouple, it can improve performance. And as I said, we have this reservation station, instruction windows. So depending on the type of processor, some processors, such as IBM PowerPC, they implement full reservation station. Each function unit has its own reservation station, or Digital Alpha or Intel processors implement. It's not centralized, it's a little bit of distributed instruction window. So they may have integer instruction window and floating point instruction window and so on. Okay, so you have instruction window. This is to wait, and instructions have to wait in this instruction window until sources are available from the function unit. Okay? And then the other buffer we have not studied is called the reorder buffer. This actually is between write-back stage. We have discussed until the write-back, but actually in the dynamic pipeline you need additional stage called commit stage. And this reorder buffer exists between these two stages. And to understand reorder buffer, you have to understand exception and interrupt. because whenever there is an exception or interrupt, the problem is complicated. And exception or interrupt should be handled as same as in non-pipelined machine, as same as in sequential processors. Okay? Because sometimes this instruction have not completed, but if you generate exception for the future instruction, okay, sometimes it can cause problem or complication. Because later this instruction can cause exception and you are handling exception for the future, which is not accepted. You have to report exception in program order. You have to handle this exception in program order. It is called precise exception. And before we go into the so in this PowerPC example, you have this kind of reorder buffer. Okay, so we'll discuss what is reorder buffer. So in this PowerPC example, we have instruction queue. This is decoupling queue between front end and back end. You have reservation station, okay, for each functional unit, and you have reorder buffer. Okay, 3 types of instruction buffers. Okay, so before we discuss exception, let's discuss register renaming more, because register renaming you can implement with Tomasello algorithm, or there are other ways of implementing register renaming. Okay. So register renaming removes anti and output dependence. Anti-output dependence. So in Tomasello algorithm, reservation station provides additional storage to remove this name dependence. Name dependence means false dependence, such as anti or output dependence. And sometimes you can use reorder buffer for register renaming, but we can discuss this later because you don't understand reorder buffer. But more common implementations, there is a separate mapping table with separate physical register file. This is more common implementation for register renaming, and it's used for Intel Pentium Pro or Pentium 4, and also digital processors. Okay, so the idea is it's a little different from reservation station. Reservation station instruction window for each functional unit has its own storage for its source and destination. So they have additional storage. They can eliminate this false dependence. In this register map table, they have a separate physical register file. So it's different from logical register file. When you program, you are programming using logical register. And without register renaming, you actually have the same set of register in your physical register file. But in out of order or dynamic pipeline, actually to remove this anti and output dependence, you have a separate register file called physical register file, which is much bigger than logical register file. So since you have more storage in your physical register file, you can do this renaming. You can allocate, every time you are trying to write, you can allocate a new register from the physical register file, so that you can implement single assignment rule, and you can eliminate write after read or write after write dependence. So you assign one physical register for every instruction with a destination register. If there is instruction that are trying to write to a destination register, you allocate a new register. Then you can essentially eliminate all this anti and output dependence. Okay? So approximately, if in the pipeline, if there are 80 instructions in flight means they haven't finished it, they haven't completed the execution, they are in the pipeline, in each of the pipeline stage, then approximately you can allocate about 80 physical registers, because assuming each instruction has a destination register. Okay? But sometimes branch or store, there is no destination register. Okay? So they don't require physical register for their destination, because it's not writing to a register. But except branch and store, every instruction has a destination register. And physical registers are single assignment register, which means every time instruction is trying to write, you are giving, the system gives you a new physical register from a physical register file. Okay? Okay, so register renaming structure is like this. This is for Intel processors. So you have map table, you have free list, you have dependence checking logic, and map modification. The basic idea is start from here. So you have a set of physical registers. Physical register. Every time a new instruction comes into a rename stage, you look at the destination number. Okay? For each destination, you allocate from the free list. Free list contains a list of free available physical registers. Okay? You select one because it's free, and you assign a new physical destination for the logical destination. Okay? So every time you are trying to write, let's say you are trying to write R1, you look at this physical register file, there are some of free available registers, you allocate maybe physical register P17. Okay, this is the first physical register you allocate. Whatever. Okay? And this map table contains this mapping. R1 corresponds to physical register P17. Okay, it's a mapping table. Okay, so for each destination, you allocate a new physical destination. Okay, to follow single assignment rule. For each source, you look up this map table. Okay, so this R1 is actually mapped to physical register 17. Then the source number should be renamed to physical register P17. Okay? 알겠죠? It's simple. Every time you are write, you are giving a new register and you maintain this mapping in the table. And if somebody is trying to read, then you look up the map table and let him know that you have to use this number, because I allocate this physical register before. Okay, that's the function of the map table. Okay, and these two. But for multiple issue superscalars, there are a little bit of complication. Assume that you have two instructions, such as Pentium, okay, dual issue. And each one is writing, so you allocate new physical register, and you look at the source, and look up the map table, and for each source, you translate the logical source register number to physical register number, okay? But one issue is there might be a dependence between these two instructions, okay? This instruction is writing to logical register 7, and this instruction is reading from logical register 7. And you just allocate a new register to logical register 7. But if you look up logical register 7 from the map table, it's the old map, right? So in this case, instead of this mapping information, you have to use this new physical register for this source. So you have to modify your mapping information by checking this dependence, right? This is true dependence checking. Okay, if there are dependence between the instructions that are simultaneously issued in the same cycle, then you have to modify this mapping. Okay? Map modification. Okay. So sometimes if there is 1, 2, 3, 4 instructions, you have to check the dependence between, let's say we have 3 instructions, the dependence needs to be checked with this one, and this is the early instruction, so this one and this one, okay, and this one. So 1 and 2, so 3, you have to check 3 dependence among 3 instructions. So if you have 4 instructions, 3, 2, 1. So it's actually, if you have n instruction, then 1 plus 2 plus blah 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 plus n minus 1 relationship. Okay? So if you sum it all using sigma, so it becomes sigma n times n minus 1 divided by 2. Okay? So it's quadratic. As you increase the number of instructions, the dependence checking logic becomes quadratic in terms of complexity. Okay? Because you need to check more and more dependence. Okay? Anyhow, based on dependence checking, you need to modify the map, and then using this new physical source and physical destination, you have to read after the rename stage. Okay? Because actual registers are physical registers. 쉽죠? Okay, let's look at the real example for Pentium Pro. And Pentium Pro, this table, mapping table, is called register alias table. And this is the logical register number. Actually, x86 has only 8 logical registers. But the physical register, there are more sets of physical registers. It depends on the implementation. So how many issues and how deeply is pipeline. Okay, so these instructions come to the pipeline. Okay, so for each source, you look at the map table. EAX is mapped to R32. You translate EAX to R32. EAX R32, EBX R30, ECX is same as logical register. Okay? Okay. So there is physical register, and there is also retired register file, which is same as logical register. Okay? This is more intermediate step for computation. Okay, so you change the source by looking up the map table, and then you need to allocate new destination for each write. Okay. So first EAX is you allocate R33, second EAX you allocate to R34. Okay? So for each write you allocate a new destination from the physical register file. Okay? But the problem is there is a read after write dependence. Right? If you look at the original instructions, okay, among the two instructions. So you actually, both EAX reflects R32 and from the map table, but you allocate R33, R34, and this should not be R32, which is the previous value. This is correct, but this should be this one, right, because of this dependence. So you need to update this one with R33. This is map modification based on this true dependence checking. Okay? But at the same time, you have to think about some instructions have committed, retired with committed, and write into the retired register file. So R29 and R30 have retired. So you look up the mapping, but because of this this commitment, this R30 should be changed to EBX because these are occurring all simultaneously. Some instructions commit, retired, and some instructions are new. So you have to also reflect the retirement status in your register renaming. Okay? Okay, so let's look at this PowerPC processor. So there is an instruction cache and fetch unit. So it doesn't show branch prediction, but there should be a branch predictor also. So this actually corresponds to front end, and branch correction is coming from the branch execution unit. After they execute, they need to sometimes correct if there is a misprediction. Okay, so after the front end, they send the instruction into the instruction queue, which is a decoupling queue between front end and back end. It has 8 entries, so you can put 8 instructions in this instruction queue. And here you dispatch, it's actually issue. So depending on the processor, as I said, sending an instruction to the instruction window is called the issue. From the instruction window, you are dispatching to the backend. Without out-of-order pipeline, sending to the backend is called the issue. But now issue is divided into 2 steps, sending to instruction window and dispatching to the function unit or backend. But depending on the processor, they switch this terminology. Sometimes they call dispatch and issue. Some processors call them issue and dispatch. Okay? So in general, it's more issue and dispatch, but here they call it them dispatch to the reservation station and then issue. So it's some inverse convention. Okay? The convention is different, can be different. Anyhow, from instruction queue, if there are available entry in the reservation station, and depending on the type of instruction, you're issuing 2 different instruction window or reservation station. These are integer ALU, these are memory, these are floating point, these are branch. This may be, I don't know, memory address or some other function or multimedia execution or something like that. Okay? Each function has its own reservation station. Okay? And these are integer unit, and this is floating point unit. And memory is dealing with both integer and floating point. So if you look at the connection, these are connected to this integer register file, floating point unit and memory are connected to floating point register file. And memory should be connected to both integer and floating point. Okay? So from here, depending on the type of instruction, after you decode, you send to different reservation station. When you send reservation station, you read all this available operand from register file and put it into your reservation station so that you can eliminate write after read dependence. And also reservation station, you have a storage for the destination. So you can eliminate write after write dependence as well. Okay? And there is a data bypass bus that go into each reservation station and also into the register file. And this is also floating point result bus go into the reservation station and also into the register file. Okay? Okay. So before I continue, let's try to figure out what is this reorder buffer. Okay, reorder buffer. And to do that, you have to understand exceptions. Okay, let's move the fourth topic, which is interrupt. and precise exception. What is interrupt? What is interrupt? We can define interrupt as a forced transfer of control. Forced transfer of control to a procedure. And this procedure is called interrupt handler or exception handler. And this kind of forced control transfer can occur because of two different reasons. One reason is called because of external event, such as I/O interrupt. Okay, or if you put the reset button. Okay, this is called external interrupt or interrupt. Okay, or the second type of event is internal event generated by an instruction execution. And sometimes the instruction execution generates some erroneous condition. The processor can no longer handle that instruction execution because of this exceptional condition. Okay? The example is TLB miss or page miss that require operating system to bring the page from the disk drive into the main memory so that processor can read the instruction from memory, because the processor always assumes instruction or data should be in the memory, main memory. If it's in the disk, then it has to be stopped. The control goes to the operating system eventually, and the OS should find the page from the disk drive and read it into the main memory. And then the instruction should restart. Okay, this is called exception. Okay? So, exception is generated by currently running process, by the current instruction. Okay? Due to an erroneous condition. So it's somewhat synchronous. If you start from the same state, every time exception, some instruction is causing exception. Even if you restart, the same instruction should generate the same type of exception. Okay? So it's synchronous. And it's internal. It's CPU internal event. It's caused by process, caused by the current instruction. Okay? Interrupt is different. It's nothing to do with current process, current program, or current instruction. It's something happened in outer space. Okay? Such as if you do a keyboard stroke, or if you put the reset button, or something like that, some outside the event, they have to notify the processor there is an event, you have to handle this event. Okay, that's the interrupt. Okay? And this is asynchronous because it can happen at any time. Okay? It's not caused by an instruction, it's the external event. External event. And general interrupt handling mechanism is you should allow interrupt or exception to be handled transparently to the executing process. Okay? So this means even if some I/O device causes some DMA interrupt or whatever, I/O interrupt, after the processor handles that event, you go back to the stop the instruction, and then the program or the process should continue without loss of continuity, without nothing happened. Right? You just handle that event and you go back and resume. Okay? Or page miss. Even if you do a page miss, after OS brings the page into memory, you go back to that instruction, you restart the instruction, and you just feel nothing happened. You can continue. You can continue. So this interrupt or exception to be handled transparently. The procedure is when an interrupt or exception is received, the current task is suspended because you need to do a control transfer by force, okay, to a handler, and the transfer goes automatically goes to a handler. So for each event exception, there are many different exceptions, and for interrupt, there are many different interrupts. For each exception or event, there is some interrupt vector or exception vector, which means some identification number. The system knows what kind of event happened based on this. So system generates some specific number, interrupt vector. Based on the interrupt vector, they can identify the handler for that event. Okay? So they jump to the handler and they start to execute handler. This is exception handler or interrupt handler. This is usually called firmware. It's not operating system code. It's firmware. It's usually in the flash. So these codes are defined by Intel designers, not by Microsoft people. Okay, and then from this handler, so there are multiple levels of this firmware. So it's sometimes called processor abstraction layer (PAL), sometimes called system abstraction layer. So they have some kind of layers, and then eventually, if it's page miss, they should call operating system. So depending on the type of OS that is currently running on the system, they might call API for Windows, 64-bit Windows, or they might call Linux or operating system API to handle that event. Okay? But this intermediate code is exception handlers, and these are called firmwares. Okay? After the handler is complete, after they process all this, then they should go back to the interrupted process, interrupted task. And this interrupted task resumed without loss of continuity. Okay? So they handle this external interrupt and they go back and they restart as if nothing happened. Okay? Or page miss, after handling page miss, they go back and restart. But sometimes recovery may not be possible because sometimes there are some severe malfunctions or some problems. Okay? In that case, the current running task should be terminated. So if the process is trying to do some illegal operation, okay, it's trying to do a write to a read-only page, you can, by looking up the TLB, you can check this operation is actually violate access permission. Okay, so it generate access violation exception, and the process should be terminated. Okay, there are sometimes hardware errors, such as cache or bus. You have parity error, which means the storage in the memory or bus there is some problems. Then the handler should examine the status. If the same error occurs again and again, then that means it report maybe cache, the first level cache bank 0, there is a error. You have to replace the bank to continue, and you have to stop. Sometimes you have to terminate the entire system, or sometimes you need to terminate the process. Okay. Let's look at exception first. Exception, as I said, this is internal processor internal event generated by the current process. Exception can be classified into three different types: fault, trap, and abort. Fault is, the characteristic is you cannot complete the current instruction. You cannot complete the current instruction, and this is reported during the execution of this faulty instruction. You cannot complete. There is something wrong in this instruction. So since you cannot complete, after this fault is handled by the exception handler, you should go back to the faulty instruction and you have to restart. Okay? That's the fault. The most common example is this virtual memory faults, such as TLB miss, page fault, or protection violation, or access violation. TLB miss or page miss, sometimes you need to translate. TLB miss means you need to translate virtual address to physical address. You have to look up the page table to find the virtual page number corresponding physical page number, but you actually use TLB. This is a cache for page table entries. By looking up the TLB, you can translate directly from virtual page number to physical page number. But TLB is a cache. In the beginning, you have a TLB miss, right? Then on the TLB miss, the operating system should be invoked. So TLB miss handler eventually called operating system API, and OS finds out the page table for the process and find out the page table entry and insert into the TLB. And then it goes back to the faulty instruction. The second time, next time, the instruction restarts, it can find the translation entry from the TLB. Okay, it can continue. Okay. Page miss is about the same. Okay, in this case, you can do the translation, but the actual data or instruction is not in main memory. It's in the disk. So it generates page miss. The operating system should bring the page into the main memory. Okay? And illegal operations such as invalid opcode, some floating point exception. You do a square root of minus number or something, and misaligned reference. Misaligned reference, the memory address generated by the processor is not aligned. Aligned means all the objects in the memory should be aligned. If it's instruction is, if its instruction is 4 byte, the address of the instruction should start at 0, 4, 8, 12, 16, and so on. If it's double floating point number, it's 8 byte. The address should start at 0, 8, 16, and so on. But if the address of the floating point data is not in this aligned address, then it can cause exception. It depends on the processor. Sometimes they don't allow and process is terminated. Sometimes they might allow and it slow down. Minji, you're on the stack top. Trap is different from fault. So fault, you go back to the faulting instruction, but trap, you go back to the next instruction after the trapping instruction. So this is more, this is actually reported immediately following the execution of trapping instruction. And this is used for debugging, breakpoint or debug. So trap means, let's think about the debugger. So on a debugger, you try to stop this process at particular instruction. There can be a memory load to a particular address, or there can be some branch instruction. You are trying to look up branch behavior, or you are trying to examine some memory data. Okay? So using the debugger, you can stop the instruction at some memory instruction. Okay? So they complete the load instruction. Right after load, they suspend the process and the transfer goes to the debugger. Okay? From the debugger, we can examine register or memory state. Okay? After we resume the process, the instruction should go back to the next instruction after the load instruction, because you have completed memory operation. Okay? So you are trying to stop the process at particular point using this debugger. And this is an example for the trap. So you report immediately following the execution of trapping instruction, and the transfer goes to the next instruction after the trapping instruction. So this is the main difference between fault and trap. If the control goes to the next instruction, it's a trap. If control goes back to the faulting instruction, then it's a fault. Okay? So if the jump instruction is causing a trap, the next instruction should point to the target of the jump instruction. Okay? Not the next sequential fetch address. You should go to the target, because that's the next instruction. Okay. The third type of exception is called abort, which means something severe errors or malfunctioned, something severely wrong. Okay, it's called abort. The example is called bit error, parity error, or inconsistent or illegal value in system table. There are some processor internal hardware registers which is not visible to the user programmer, and sometimes that state can be corrupted, and the hardware monitor the registers and it can report this kind of exception. Okay, or sometimes this is hardware errors. Okay, in this error you cannot continue because of this problem. This is more severe problem. You have to suspend the process and suspend process at unpredictable location. Before sometimes you can, most of the time you can continue, and you have to stop at the right point, right? Because you need to continue, you need to recover, but you don't have to worry about the recovery because it's not recoverable errors. Okay? So it does not report precise location of instruction causing the exception, and the program does not restart. Something very substantial happened. And the exception handler is called the abort handlers. And they collect diagnostic information about the processor state, and they perform graceful system shutdown, which means, let's say there is a parity error. Okay? It can be transient error. Transient error means if you reread the bank, next time the error disappeared and it's okay. Okay? Then you can go back. Okay? But sometimes it's permanent error. The bank should be replaced. Okay? So to identify whether this is permanent or transient, the abort handler should re-examine the state, okay, the cache state, and re-execute some diagnostic instructions, and then it should figure out whether that has severe errors or it can be recovered. If it cannot recover, then it should report this state and it should terminate the process, and sometimes shut down the entire system because of this malfunction. Okay? This is called abort. And sometimes you can generate exception using an instruction. The example is INT instruction in x86 processor, and using an exception number you can generate some exception. So this is actually it's similar to procedure call to an exception handler. Okay, this is called software generate exception or software interrupt. Okay. So all exceptions except abort must report the exception on a precise instruction boundary, which means for a fault, it should report fault at the faulty instruction. So next time when you go back to the resumed process, you should restart from the faulty instruction. Okay? If it's a trap, then you should go to the next instruction, because trap means you have completed the trapping instruction. You should go to the next instruction. Okay? So precise exception model means all integer and floating point exceptions are reported on the faulty instruction. All previous instructions should be completed before the exception point or interrupt point, which means if this instruction causes an exception or interrupt or exception, that means you have to restart from here, but you have to wait until this completes, because you have to wait until this complete. This should have completed, and then you have to report the exception. Okay, and all subsequent instruction, the future instruction, you have to nullify, you have to remove, you have to flush, because you need to restart anyway. Okay, so when you go back, you are starting from here, and this should be completed. Okay. So all previous instructions should be completed before the interruption point, and all subsequent operations should be nullified. And after handling the exception execution resumes at the faulty instruction or at the next instruction, depending on the type of exception. Okay? Okay. Let's look at the exception handling mechanism further. Exception vector. So as I said, each exception or each interrupt is associated with an identification number, and this is called interrupt vector or exception vector. Okay? So whenever there is a page miss or TLB miss, page miss might be exception 19, TLB miss might be exception 17. For each processor, there is a definition of event number and exception vector. Okay, this is defined in processor's reference manual. So if you look up the manual, it defines all different type of exceptions that can happen and all different type of interrupts that can happen. Okay? And this is called the interrupt vector. And this is some hardware generated identification number. From the vector, the hardware can identify the exception handler address, okay, by mapping. So there might be a table using the vector as an index. You generate some address of that exception handler or interrupt handler. This is the normal exception procedure. So on an exception, you flush all the instruction fetched subsequent to the instruction causing the exception. So if this instruction is causing an exception, you have to flush all the instruction behind, right? Because you have to restart anyway. You have to flush. You have to drain the pipeline, complete all previous instructions. You have to wait until all these previous instructions retire. Okay, they should have completed. And you complete all outstanding write operation prior to the faulty instruction. And then you have to save the program counter of the next instruction to execute. So if this instruction is a cause an exception, if this is a fault, you have to save the address of this instruction. If this is a trap, you have to save the address of next instruction. Okay, because you have to restart from here. And you also need to save the registers and stack pointers to restore its state. After the exception handler, when you go back, you have to start from the same state, which means you have to save the register state as well. Because the exception handler will use the registers also. Okay? So you save your context, you vector the interrupt. Vector the interrupt means using the hardware generated exception vector, you identify the handler address. That's called vector the address. Interrupt. You fetch instruction from the interrupt service routine, which is an interrupt handler or exception handler, and service the interrupt or exception, and then you return from the interrupt. Okay? So this exception handling is actually processed by the kernel. Okay? So you switch to user mode to kernel mode. After you handle the exception, you go back to the user mode and continue. So this return from the interrupt, there is usually a separate machine instruction called return from interrupt instruction. Okay? It's not same as procedure return. It's from kernel to user transfer return. A little different. Okay, let's look at interrupt. Interrupt is, as I said, is asynchronous. Asynchronous. It can happen anytime because it's outside event. You have no control. Okay? And it's caused by external event or IO device. And you return to the next instruction for a restart. Interrupt, so trap means you have completed. And fault means you have not completed, you have to restart. So every cycle there can be an interrupt, trap, and fault. Okay? And it's somewhat complicated. So what is the interrupt point? Interrupt point is in the middle. So trap should be completed, right? So you have, this belongs to the previous instruction. Interrupt point is like this. Every cycle boundary, you check the interrupt. This is before your fault. Okay? Fault is somewhat in time order. You have to go back and you have to restart. This belongs to the future. Okay? This is the past, future, interrupt is in between. So if you have 3 events at the same time, you have to handle trap first, interrupt, and then fault. Okay? And interrupt, it depends on interrupt. If this is non-maskable interrupt or some hardware reset, then you have to handle this interrupt first. This has highest priority. But otherwise, this is maskable interrupt, then you have to process trap, interrupt, and fault in this order. So interrupts are classified by maskable interrupt, non-maskable interrupt, and software interrupt. This is software interrupt I have discussed in the exception using INT instruction. Okay? So it's essentially classified into maskable interrupt and non-maskable interrupt. Maskable interrupt means it can be disabled or enabled by instruction. You can enable external event, external interrupt can happen, you can disable. Sometimes you need to disable. If it's some synchronization or some critical section, you want to disable other external interrupt to happen because critical section should be complete in an atomic way. Okay? So you can disable or enable. So maskable interrupt means you can disable or enable by an instruction, by software. And this is generated by asserting interrupt pin or sending interrupt message over APIC bus. Interrupt pins on the CPU package, there is 2 different interrupt pins. One is INTR pin, the other is NMI pin. So whenever you generate some more important interrupt, you use NMI pin. This cannot be masked. This requires immediate attention and immediate handling by the processor. Okay? The general interrupt, you use this interrupt pin. This can be disabled by the processor if they are doing important operation. Okay? So this is generated by asserting an interrupt pin. And usually, before in the past, Intel had this 8259 programmable interrupt controller that delivered this interrupt vector on the system bus. You assert interrupt pin, at the same time you generate interrupt vector and put it in onto the system bus, processor bus. So it notifies what kind of event you are generating because exception vector or interrupt vector is the identification number for the event. And the I/O device put this event number on the system bus so that processor knows, oh, I need to handle this kind of event. So using this number, they can go to the handler, okay? Because they can map from the vector to the handler address. 졸고 있는 민지 알아들었나? Non-maskable interrupt cannot be disabled by program, and it's received on the separate NMI pin. It cannot be disabled. So you have to handle this exception or interrupt immediately. And software interrupt, as I said, this is caused by INT instruction in x86, and using N is an interrupt vector number or exception vector number. You can actually call exception handler or interrupt handler directly. This is something like implicit procedure call to an interrupt handler. Okay? And because it's done by software, you don't have to mask this interrupt. Okay? Interrupt priority. So hardware reset or abort has the highest priority. Abort means you should shut down, or hardware reset means you have to reset. You have to start from the beginning. This has the highest priority. So whenever this happens, you have to handle this event first. Okay? And then external hardware intervention. Init is something like hardware reset, but without flushing cache. It's similar to reset. And SMI is a system management interrupt because of the power management, and so sometimes you shut down the processor, shut down the monitor, and so on. This is another important interrupt you have to handle. So these are more important events. And then you handle trap. Okay? This is when for multiple issue processor, different events can happen at the same time. Okay? You might have trap or fault in the same cycle, or at the same cycle, at different pipeline stage, you might have ITLB miss. You might have execution stage, you have data page miss. You might have trap for branch instruction. You can have external interrupts, one from maybe mouse and one from hardware reset, all occurring at the same time. Then you have to handle this interrupt properly, and you should follow this priority, and you also need to follow program order. But interrupt is nothing to do with program order, right? So they define this priority for external interrupt. So in general, except these important events, you handle trap first because trap belongs to the past, okay? And then external interrupt, and then fault. Fault belongs to the future because you have to restart, okay? For the fault, you have to handle this fault in program order, okay? So if there is an exception on the execution stage and exception on the fetch stage, which exception should you handle first? Minji. Let's say 2-issue Pentium pipeline. You have a data page miss at the execution stage. You have a TLB miss, ITLB miss at the fetch stage. Okay? Which one would you handle first? Why? You have to handle exception in program order. Otherwise it's complicated, right? Sometimes if you handle this exception first, then before you process this instruction, you are handling exception for the future. When you restart, what do you do? Right? Sometimes you are going to different paths, and you are doing exception for some instruction that you don't have to handle. Okay? There might be misprediction or whatever. So you have to handle exception in program order. Okay? So you have to handle exception at the execution stage, and then decode stage, and fetch stage, and so on. Okay? In program order. And lower priority exceptions are regenerated after returning from the higher priority interrupt handler. Okay? These are interrupt priority mechanism, and they usually use this centralized arbitration. And it's same as bus request grant logic. You can view this as interrupt request and interrupt grant. Okay? Assume that you have 3 I/O devices. They are requesting interrupt. And sometimes you assign highest priority to this device, and then this is second highest priority, and this might be the third highest priority. Okay? So maybe this has highest priority. This grant logic, this is input, this is output. So if you look at the truth table for this logic, this is combinational circuit, and this is actually priority encoder. Okay? If this is 1, you don't care, this should be 1 and this should be 0. Okay? If this is 0 and this is 1, you grant this interrupt to this device, no matter what this has. Okay? And so, if this is 0, this is 0. If this is 1, then you grant. Okay? So this is very simple logic. You can implement very simple central arbitrator or parallel arbitrator using small combination logic. And this is called daisy chaining. You can connect this I/O device serially. Okay? And this bus request or interrupt request go into wired OR logic. Any device is requesting an interrupt, then it goes to interrupt request. Grant goes to the first higher priority device. If this device has requested before, you grant this device first. If the device has not requested the grant goes to the next device and so on. Okay, this goes serially. So in this chain, the first one has the highest priority. This is second highest, third highest, and so on. This is called daisy chain. Daisy chain. This is basic computer architecture undergraduate level. Okay, the third type is called software polling. So anybody is requesting, this arbitration unit is polling each device in priority order. So if this has the highest priority, do you want this? Do you want interrupt grant? Did you request? No. Did you request? No. Did you request? One by one. And based on this order, this is called polling, software polling. Okay, so we use this one for interrupt grant logic. Okay, and then we move to the processor internal logic to implement this precise interrupt. Let's have a break before we discuss this detail.